Hi everybody, welcome to my 18th axial bar video. In this video I'm going to be talking about how to find the stress in this bar as a function of x if it's subjected to this increase in temperature given by this equation. Then after that I'm going to solve this question, very similar but with the introduction of a spring. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. In order to solve this question, we need to use the differential form of the equation we've been using so far to find the displacement due to a thermal. So this is what we've been using so far. Delta is alpha times delta t times the length of that piece. But this is for a piece of material of length L. If we imagine shrinking that piece down to length dx, we get this equation here. D delta is equal to alpha delta t dx. Okay, you can see my first video on thermal effects to see a more in-depth explanation of this. So this equation allows us to find delta if alpha or delta t is varying as a function of x, which in our case it is, according to this equation right here. So if we take a look at this bar, traditionally what we'll be doing is taking a cut, looking at the internal normal forces, then going ahead to find any displacements. But in this case, there's no forces being applied to this, so we can't really go in and make a cut to find the internal forces. What we can do is take a look at a small section, alright, a distance x away from the origin. Alright, so this piece here will be of a length dx, and the elongation of that piece, d delta, is equal to alpha delta t as a function of x, so whatever the increase in temperature is at that specific point on the bar, times dx. So that's the displacement of that piece. So to find the total displacement, we sum up all the displacements. Alright? So delta, we're going to get our answer as a function of x, so I'll write it as such, equals to the integral of alpha delta t as a function of x. That's this right here. Delta t2 x cubed over L cubed dx. Okay. And then we go ahead and integrate this, becomes x to the 4 by 4. So then our final equation for delta as a function of x is alpha delta t2 x to the 4 over 4 L cubed. Alright, so I'll make it kind of a tentative box around here, because this is not what we're looking for. We're looking for the stress. Alright, now you might be wondering, how in the world can we find stress if we don't have a normal force? Because we're used to finding stress as normal force over area. But let's take a look back at our definition of Young's modulus, alright? E was stress or strain. Alright, and we can write strain, rewrite this way. E strain. Alright, and strain was just delta by L. Alright, so plugging this back into here, we can say sigma as a function of x is equal to E by L delta as a function of x. Right? This could be functions of x too, but in this case they're not. So, well, check it out. We've already found delta as a function of x. So all we got to do, take this, plug it in here, and that's our answer. So the stress as a function of x is equal to E alpha delta t2 x to the 4th over, we have an existing L, times 4 L cubed. That's going to be 4 L to the 4. Alright, isn't that a beautiful answer, really? I mean, I find it so fascinating when you have something varying like this, and then you do some calculus and some mechanics of materials, and you can find this out. Okay, so let's move into the next example that I showed you in the very beginning, where this problem takes another big step up and we introduce a spring into here. So now how are we going to find sigma as a function of x? All right, it gets a whole lot more challenging. All right, so we're going to follow the same process we did before, but now we're going to have a normal force. If you recall before, we didn't have a normal force, but in this case we will because the spring is going to contribute some force. Okay, so if you imagine, now that we have a force, we need to make cuts. All right, so we'll cut here. You cut, I don't know, here. Look this way. All right. Now, I'm not going to go through the whole effort of writing a free body diagram, even though I probably should. Because since we only have one force from the spring, we're just going to think about this using common sense. We're going to have a reaction at the support. All right, we can imagine a free body diagram of this piece. You have an internal reaction pulling away, the reaction pulling away that way. Therefore, the R, let's just call R at 1, is going to equal to the force in the spring. Right? Now let's look at this piece here. We have a reaction pulling away again. We have the internal normal force in here. The internal force in here is equal to this, so the only two forces. Alright, so if it's equal to R1, normal force, alright, equal to R1 equal to Fs. These all three are the same, so the force throughout this thing is the same. Alright. So now if we want to find displacement, well, we have a statistically indeterminate situation, and the displacement in this situation is always sum of d delta is equal to 0. And in this case, we have two things contributing toward displacement. We have a displacement of the spring piece. All right, that's going to be moving. So try to treat the spring as it was another chunk of bar, not like this some scary looking spring. All right, so the spring is going to be doing something, and the bar is going to be doing something in two ways. All right, we have a force displacement and we have the temperature displacement. So let's just write this here. Delta from the spring plus delta in this piece due to the normal force plus the delta in that piece due to the thermal. And somehow one of these, so this arrangement has to equal 0 because we have fixed supports. Okay, now let's move in and put our variables and see if we can get some sense happening here. So to look at the displacement of the spring, let's go back to some grade 11 physics. F equals kx. All right, that's the displacement of a spring. So in our case, the displacement delta is the x here. All right, so we can write x. We'll replace delta with x, or x with delta. Delta is equal to F in the spring over k. All right, and we know k. Well, we don't know it, but they told us that we could know it. All right, so it's given to us as a variable, so we can totally use that. We can plug it into here, Fs over k plus the normal force in this piece. Well, the normal force is going to be constant throughout, right? We kind of seen that in this equation here. The force is constant. So we can just say the normal force times the length for AE plus the temperature displacement. All right, now in the last question, we already found the temperature displacement. All right, it was this here. Boom. So I'm just going to recopy that in here as if I had, done the whole integral again. All right, so it turns out to be E alpha delta T2 3. This all equals 0. All right, now we want to find the stress. All right, so in this case, our stress is going to have something to do with the normal force by area. So we have normal force here, no normal force here. That's okay. This is all like something we can deal with. Just x and then variables. This Fs, wait, that equals to n. So let's just scratch that, replace it with an n. So we'll factor out the n out of these two, move this blob onto this side, and divide through by this remaining piece here, and we're going to get normal force as a function of x. And as a function of x equals, this blob is a negative alpha delta T2 x to the 4 over 4L cubed, and then divided by what's left of this piece here after we factored out n. So it's going to be 1 over k plus L over AE. All right, there we go. And that's a normal force. Now we were asking for the stress as a function of x, and we just said the stress is the normal force divided by the area. So we can just go through, divide this by the area. It's the same as like timesing this by an A. All right, so then it gets stress as a function of x equals to E alpha delta t to x to the 4 over 4L cubed. All right, times A. All right, you can put this in, put this out, however you want. Put it here, why not? There we go. And if we want, we can rearrange this with some algebra times the top and the bottom by EA, just to get rid of this. And then finally, we can write the stress. The function of x is E alpha delta t to x to the 4 4L cubed E A by K plus L. All right. Box this off. Now let's do a quick check, because if this spring was theoretically part of the bar, we should get back the same equation that we got in the first half of this. So in order to make that true, we can imagine K going to infinity. All right, so K goes to infinity, becomes really, really so stiff, it's the same as a bar. This piece goes to 0. We're left up with 4L cubed, 4L to the 4, E alpha delta t to x to the 4. Bango, exactly what we had here. All right, now this is, I just think this is so cool. All right, like, let's just call it beautiful, because it is. Okay, think about it. We had this like funny looking situation. We had some varying forces, a bunch of calculus, and we got an answer. All right. So anyway, enough of my little bit of nerding out there. Quick review of how we solve these questions. Let's take a look at the first question we solved. And we said, okay, the temperature increased causes some sort of displacement, and we found that by looking at a differential form of this, we integrated, we found the stress by using the Young's modulus relationship, and we essentially did the same thing for this question here with the extra spring, except in this case we had to deal with forces. All right, we used the sum of displacements to be 0, added it all up, factored it all out, and found that the stress as a function of x is actually the same as the first one if we take K to be part of the bar. Alright, hope you guys enjoyed this video. Thanks so much for watching, and I'll see you in my next axial bar video.